டைரக்டா நம்ம வந்து டெஃபினிஷன் ஃபார்முலா அது ஜம்ப் ஆகிறதுக்கு முன்னாடி வாட் இஸ் பவர் ஸ்பெக்ட்ரல் டென்சிட்டி? சே PSD, power spectral density, that means how the power is distributed in the bandwidth. Say whenever we are operating with some system, we will be given some bandwidth, we will be given some power. So the entire power will be within that bandwidth. So what is PSD? PSD means how the power is distributed in the given frequency. Okay, so what this is indicating, how power is distributed, how power is distributed in the given frequency, in the given frequency range, in the given frequency range. Again, this may be uniform or non-uniform. The distribution may be uniform or it may be non-uniform. We do not know. We do not know. Power வந்து யூனிஃபார்மா டிஸ்ட்ரிபியூட் ஆகலாம், நான் யூனிஃபார்மாவும் டிஸ்ட்ரிபியூட் ஆயிருக்கலாம். என்டையர் பவர், say uniform in the sense the entire power may be distributed like this. This is the uniform distribution. Non-uniform means say it may be distributed in some random manner. I do not know. Okay, see, this is the frequency axis. X-axis is the frequency. Then this is the PSD, power spectral density. Power spectral density. So this power spectral density may be uniform and it may be non-uniform also. The notation for power spectral density is Sx of S of f. Okay, usually this is notation is S of f. Power spectral density notation is S of f. So y-axis is S of f. So I'll write here S of f denotes the power spectral density. Mathematical notation is S of f. Okay, how the power is distributed to each and every frequency. Again, what is the unit of PSD? Okay, power divided by bandwidth. So this is watt per hertz. Okay, the unit of power spectral density is watt per hertz. Watt per hertz. Okay, so now how can I relate power with the power spectral density in general? If it is uniform, that is very simple. I can multiply y value with the bandwidth. Okay, with the x-axis bandwidth. If it is uniform, but if it is non-uniform, I cannot do. So you see, what is the, if you try to find out the entire area, this entire area will give the actual power because the entire power is distributed within this frequency in this manner. Similarly, the entire power is distributed within this frequency in the different manner. Again, this is also the entire area is giving the power. So now power is equal to integration of S of f with respect to df. Integration of S of f df. That means if you integrate the power spectral density with respect to f, that will give the power. Okay, if it is the uniform, uniform means it will have only one value. So that PSD you can directly multiply with the bandwidth. Okay, you know what is the bandwidth. But if it is non-uniform, you have to use the integration operation. Already you know what is the application of integration. Integration will give the area. Okay, if the area is uniform, directly you can use ordinary formula, A cross B formula. Okay, or otherwise if it is non-uniform, only we have to use the integration. So again, this integration will work out for uniform also. So that's why in general we will use the integration formula. So power is equal to integration of power spectral density. So now quickly we have seen what is the power spectral density, how it is related to the power. Okay, related to power and then bandwidth. So now we'll see what is the relationship between the autocorrelation function and then power spectral density. So now I am taking some random signal, say random signal, but for that random signal, I know the autocorrelation function. Okay, I am having some random signal, but for that random signal, somehow I know autocorrelation function of that random signal. Why? Because random signal we cannot express in the time domain with help of the deterministic equation, but somehow we know the autocorrelation function nature. So again, this autocorrelation function, usually it will be in the time domain or tau domain. For the autocorrelation function, if you take the Fourier transform pair, if you take the Fourier transform for autocorrelation function, that will give the power spectral density of that particular signal. Usually that signal may be random signal or deterministic signal. Okay, for any signal, you can take autocorrelation function. It may be random or deterministic, but in general, we are discussing about random signal. For that random signal, Rxx of tau is the autocorrelation function. Then if you take the Fourier transform, that will give the power spectral density. You know that autocorrelation function is in the time domain. This will be in the time domain. That means tau domain. Okay, this is in the time domain. Power spectral density will be in the frequency domain. Power spectral density will be frequency domain. You know that Fourier transform will convert time domain into the frequency domain, and also you know the basic Fourier transform formula. So then also you know what is the notation for autocorrelation function, that is Rxx of tau. Then power spectral density, just now I have defined, that is S of f, but we are writing power spectral density for a random signal x of t. Okay, for a random signal capital X of t, I am writing the power spectral density. That's why S suffix capital X and then small f. Then we have to write the Fourier transform pair. So Sx of f is equal to ordinary Fourier transform formula. Fourier transform means minus infinity to plus infinite. Then time domain signal, that is Rxx of tau, and then e power minus j omega. Usually we will put t, but we are in tau domain, so e power minus j omega tau. Instead of dt, this is d tau. Okay, this is the relationship between the autocorrelation function and then power spectral density. Okay, for a random signal, I know autocorrelation function. Once I know the autocorrelation function, using this formula, Fourier transform formula, I can find out what is the power spectral density. Now, then I can also write it in the reverse. Okay, once if I know the power spectral density, using inverse Fourier transform, once if you know the power spectral density, you can also calculate the autocorrelation function. Say, or before that, in this formula, we will put f is equal to 0. Okay, once if you put if f is equal to 0 in this formula, Sx of 0 is equal to integration minus infinity to plus infinite Rx of tau, then d tau, Rx of tau, and then d tau. Okay. Again, can anybody tell me what is Sx of 0? What is xs of 0? Sx of 0 போடும்போது integration of autocorrelation function d tau வருது. Frequency is 0. When frequency is 0, that will give the DC component, that will give the effect of the DC. Okay, how much DC power is there? How much power is concentrated on f is equal to 0? This will directly give, see in the diagram, I am putting, say this is f. This is S of f. When I know what is S of f, that means f is 0, then it is directly giving how much value is there for f is equal to 0. That means what is the contribution of DC signal in the power? Okay, what is the contribution of DC signal in the power? This is giving the contribution of DC power. DC power. Okay, direct or indirect DC component idu vandu tharudhu. Okay, DC power. Okay, then if you write the inverse Fourier transform formula, that means once if you know the power spectral density, you can calculate what is the autocorrelation function. That we can write like this. Say I want to calculate Rx of tau. I already know what is Sx of f. Sx of f. Then e power, instead of minus, we will put a instead of usually we will put minus in the forward. In the reverse, we have to put plus. E power plus j omega tau. Here d tau or df, anybody? In the reverse, inverse Fourier transform, what I have to put? Differentiation variable. Anyone? Okay, what is present here? F. Okay, here I have to put df. Okay, I have to put df. Now you put tau is equal to 0. if tau is equal to 0, Rx of 0, then integration minus infinity to plus infinite, Sx of f df. Okay, the integration of power spectral density, I already told you, integration of power spectral density will give total power. So integration of power spectral density will give total power. So this is the total power. And then in the previous slide itself, we have discussed what is Rx of 0. What is R? So already we have defined what is Rx of 0. That is also power. That is also power. Once again, we are proving, okay, power in the tau domain in terms of autocorrelation, power in terms of the power spectral density. Both are again same. Both are again same. Okay, this is all about the power spectral density. Then quickly we will see some of the properties of the power spectral density. அதாவது ரேண்டம் சிக்னல்னாலே டைரக்டா பவர் கண்டுபிடிக்க முடியாது, இன்டைரக்டா தான் பவர் கண்டுபிடிக்கணும். விசிபிளா இருக்கா? பேசுறது கேக்குதா? ஸ்கிரீன் விசிபிள்? எனிவன்? குயிக்கா வந்து நம்ம பவர் ஸ்பெக்ட்ரல் டென்சிட்டியுடைய ப்ராப்பர்ட்டிஸ் பார்ப்போம். ப்ராப்பர்ட்டிஸ் ஆஃப் ப்ராப்பர்ட்டிஸ் ஆஃப் பிஎஸ்டி. ப்ராப்பர்ட்டிஸ் ஆஃப் பிஎஸ்டி. First property, power spectral density is always even function. Again, power spectral density is also even function. Power spectral density is even function. Then at any point of time, PSD value, PSD power spectral density value, it never be negative. Power spectral density, that is that Sx of f, it is always either 0 or positive value. It never be negative. Why? Because you know power cannot be negative in general. The voltage and current all may be negative. Power can never be negative. So that is the another property. Only two properties. One is with respect to even function, power spectral density, that is Sx of f. So what they are trying to say, Sx of f or Sx of minus f. Okay, both are even function of frequency. Then power spectral density value at any point of time, it cannot be negative, always positive. So PSD is always positive. Always positive. This is the two properties of the PSD, power spectral density. Then the next topic here is transmission of the random process through linear filter. Transmission of the random process through